In this question, we are given that there is a current. It's a current in an electric circuit. There's an electric circuit, and this current given by the symbol I. This current obeys a differential equation. It obeys this equation. For di dt equals to 2 minus 3I. So the question is to solve this equation for the current. Okay, to solve for the current, given that when the time t is 0, the current is equal to 2. So that's the first part of the question. And the next part of the question is when t is very large. When t is very large, what happens to I? So that's the next part. So it's just these two parts to the question. So let me start by thinking about how we could solve this equation for I. Okay. I should rearrange this so that I is on one side and all the t is on the other side. So let me try that. I can cross multiply those two terms, 4 and this whole thing. So I do that, and I can bring dt over to the other side as well. So I'll get di. Okay, so that comes down here, 2 minus 3I. dt goes up here, 4 comes down there, like this. So that's what we get. And then we can integrate these. We can integrate this, and in principle, this would just give t for d when we integrate dt. And if we integrate 1 over this function, a linear function of I, means there is no I squared term in there, we should get a log function. So to see what we get for this, let me just recall what we know about differentiating log. Right. So if I differentiate log x by dx, I get 1 over x. Okay, so we know that. Now, but what happens if the x is negative? You know, if you do log x, the x has to be positive. Otherwise, the log is undefined. Okay, so this only works when x is more than 0. But what happens when x is less than 0? Okay. So as it happens, we can make use of say the symmetry of this function. We make use of the symmetry of this function to say that if I think about log of the modulus of x, log of the modulus of x, and differentiate log modulus x, I would also get 1 over x. Okay, so I shan't go into the details as to why this is the case for this part, for this video. So I'm just going to make use of these results as something that we can recall, and in order to use this result here, in order to use this result here, I want to be able to integrate a function that looks like this. Okay, so if I integrate 1 over x, I will get log modulus of x. But in this case, it is not just 1 over x, or in this case 1 over I. I have this 2 minus 3i, and it's and because I have a minus sign here, okay, things is a little bit complicated. So what I'm going to do is I'm going to we can use integration techniques like substitutions and so on, and that would mean a few more steps. But we can make things a lot easier if we think of another form of this differentiating of log x. If I imagine, for example, I have instead log modulus of x plus a constant, for example, a fixed number a. Then if I differentiate this, I would get 1 over x plus a. Okay, so if we start from here, then when we change x to x plus a, we know that if we differentiate this, we can make use of this, but we also must use the chain rule to differentiate x plus a as well, and then multiply by this. But if we differentiate x plus a, it's just 1. Okay, so that's why we get this. Okay, so hopefully this is something that we can recall quite quickly if we need to do this question. So coming back to this, because we if we make use of this formula knowledge, we can make use of this by rearranging this a bit, so that so as to get rid of the minus sign here. And I can do that by factoring out a factor of minus 3 outside a bracket from the denominator. So this is what I mean. I can write it like this. If I take out a factor of minus 3, I'll get 1 over minus 3, and then here I would get 1 minus 2/3. Okay, so you can check that if you multiply minus 3 into the denominator, you would get back the previous expression. So on the right side, still the same. dt, I'll take out the 1/4. So that's what we have. So now I have a form here which is the same as this. Right? X corresponds to I, and minus 2/3 corresponds to A. So I'm ready to integrate this now. Let me bring the minus 3 over to the right. That gives minus 3/4. Okay, and if I now integrate this using this formula, I would get log of the modulus of I minus 2/3. Integrate dt, I'll get t. And because it's an indefinite integral without any limits, there would be an unknown constant. So here we are. Once we reach this step, we're ready to make use of the initial conditions. clear this off. So let's see, the initial conditions are that when t is equal to 0, I is equal to 2. Let's see how to use this. We can probably just substitute the values into here directly. Now, but in this case, it's often easier if we do some rearranging first. So this is the natural log, so it's log to base e. So therefore, if I rearrange this, I get I minus 2/3, and then e to the power of this whole lot minus 3/4 t, and I can separate that term out as e to the power of c. Okay, so now if I remove this, if I remove the modulus sign, it means that this expression, we have to remember that the expression inside might be plus or minus. We don't know yet before solving with these conditions. So if I remove the modulus sign, it is possible that the answer is either plus or minus. Now this is always plus. E to the power of a number, positive number to the power of something is always a positive number, if the power is real, of course. So therefore, since this can be plus or minus, I should add a plus minus sign there. Okay, it's because previously this is the magnitude of I minus 2/3. But now that I remove the modulus sign, it's possible that that this is actually either plus or minus. That's why I need to include this. Okay, but whether this is plus or minus, I have an unknown constant here. C was an unknown constant, but now that I have e to the power of c, I can think of this whole lot. And not just this whole lot, the whole lot including the plus or minus sign. I can think of this as the unknown constant. It's like I don't actually know whether this is plus or minus. So I can think of this whole number as part of an unknown. If I let this be a, then I can think of this as the unknown instead of the c, and try and solve for a. Okay, so let me try and solve for a now, using these initial conditions. So when t is 0, I is 2. So let's substitute. I is 2. That's a. And that's e to the power of 0, since t is 0. So we just get 1. Okay, so therefore, we have a. A is equal to 4 over 3. So now we have the answer. And I'll just substitute a and rearrange that to get I. Okay, so I minus 2/3 is equal to 4/3 for this. 4/3 and e to the power of minus 3/4 t. And therefore I is equal to, bring that over, 2/3 plus 4 over 3 e to the power minus 3 over 4 t. So we have done the first part of the question. Now in the second part of the question, we want to know what happens when t becomes very large. So when say t goes to infinity. What happens to I? Right, since this e has a negative power, so when t goes to infinity, e to the power minus t must go to 0. Okay, so that whole thing becomes 0, this term becomes 0, and we're left with 2/3. So that's the answer. When t goes to infinity, I goes to 2/3. That's it. That's the answer to the question.